Hello everyone, I'm glad to share my recent work, DecoupledGaussian accepted in this CVPR2025. Well, there is a trend in the 3D simulation that tries to simulate from the real-world objects. DecoupledGaussian, this representative work starts the trends by introducing the Gaussian splitting kinematics that try to introduce some rotation, covariance metric, or spherical harmonic coefficients. These things can be naturally adapted to the classical material point method simulation engines. After that, there is another work called the VRGS that tries to deform any segmented objects using SAM through XPBD simulation engine. However, either the DecoupledGaussian VRGS or future splitting, as we can see, their methods couldn't detach objects from their contact surface. That can be used for the variety of simulation. The core issue here is that failure to recover the occluded geometry and texture. So our task is try to do such stuff, given the input videos, and we try to decouple the object and their contact surface with the complete geometry and texture. Using this complete texture and geometry, we can support various interactive simulation. The left scene collision and right is object melting. Why we want to do this task? Since we found out if we solve it, our task can be used in the autonomous driving simulation that we usually want to simulate detach the cars, vehicles from their contact roads to prepare the dataset, also used in the entertainment industry. Sometimes we want to move the boxes from the ground plane, and also can be used for the robotic landing interaction, so to teach the robotics how to move the objects when they contact to their scenes. And last thing, and important, is to be used in VR AR interaction. Sometimes we want to move the real world objects and try to see what happens. Okay, let's go into our pipeline. In our pipeline, we have three parts. The first part is 3D Gaussian preparation. We need to prepare the Gaussians that sometimes need to use the real capture scenes and to reconstruct Gaussian splitting, and also need to segment the objects we need to move. And second is to restore the object and their context scene. And the last is using the object and the context scene after restoration to do the simulation stuff. And in the red circle, I just pointed out some novelties we have done in this work. Okay, let's go in on our 3D Gaussian preparation. One component in this way is PGSR. The goal of using PGSR is that we want to estimate the correct geometry from Gaussian and remove the large floaters in the scene. As we can see in the right figures, without the parameter-based Gaussian splitting, we can face there are lots of floaters in the scenes, and that is really difficult for the object to move efficiently. And I just concluded several points. If you are interested in PGSR, I recommend you to read detail in their law paper. Okay, and second is to do the segmentation. How do we do the segmentation? Firstly, we want to get the labels from the SAM2 and then manually select the classes in the first frame. And each kernel is assigned semantic features and a gating network to predict the segmentation results. And the right figure shows the PCA visualization results, as we can see here. And also using some local feature smoothing to make the features in the neighborhood points share the similar features. And then second step is object scene restoration. And we first using the user-specified click position to get the object. And then for the context service, we sometimes need to use the KM to remove the nearby artifacts. And the last important step is to restore the both object and context scene. Here we use join point fields, proxy points, and unitary negative cross entropy and Gaussian restoration. If you have any questions, let's go to the next slides for the details. But before I go into the details, I want to point out is that we don't using the 2D impending tools to repair the geometry, since we find that the impending regions often fail to blend seamlessly with the surrounding geometry, creating artifacts, and also the texture inconsistency across different frames due to the lack of robust video impending tools. That may be the next direction for that. So our approach just authorizing the geometry restoration using the intrinsic Gaussian spreading geometry priors to ensure a coherent surface, even when the texture impending is imperfect. Okay, let's go into our joint point fields. The geometry prior behind this is assuming both object and scene as smooth closed shapes with resort to Poisson surface conjunction, which equivalent to the within number fields. Okay, let's see the steps. Firstly, we're using the joint point fields. We're using the square Poisson conjunction to solve for different for object and the context surface independently, and then to coordinate transformation. And the last step is to solving the conflicted regions as shown in the right by curvature and prioritizing the surface. So after we solving the conflicts, then we try to extract the dense interior points for objects well, merging cubes to get the curved mesh patch for the surface. Our steps is here for the dense points. The Y is helpful for the NPM simulation, and for the patch mesh, we fix the broken geometry of the surface. So question is that how about the input to the joint point fields? There is a context surface and target object that are different. For the context surface, we're using the Gaussian centers as points. That is easy. And for the normals in the Poisson conjunction, we're using the minimal scanning as normal. But for the target objects, the sense is different since the geometry is very complex. So we're using the proxy points instead of Gaussian centers. Our proxy points is that we want to combine the information from the multi-view images, but differently from the old TSDF techniques, since we introduced the projected depth mask to boost fusion speed, obtain the projected mask by setting 0, 1 opacity, and then segment the final proxy points based on the low Gaussian kernel with the nearest neighbor searching. And for the proxy points, let's have just a quick quantitative operation as shown here that we using proxy point, we get the geometry really well. And the next step is the unitary negative cross entropy, since we found that in the Poisson conjunction, there is a trend start to expand the geometry that is over smooth the closed surface. So in order to solve that, we're using the multi-view covering strategy to cover out these floaters, these unnecessary points. And that is our formulation shown here. As shown here in the right figures that without the UNCE, our results can see there is floaters in the red rectangle. And the second is using the Gaussian restoration, is that in the last steps we just restore the geometry. But for this step, we also want to restore the texture information that need to be connected with some 2D impending tools. Even though the 2D impending tools failed to capture the good texture, but in the last steps, we are good for the geometry. And the next phase in our pipeline is to do interactive simulation. Okay, let's see our evaluation. Our evaluation is straightforward: the object restoration, scene restoration, and also to context object scene interactive simulation. Let's see the results. As shown here, our scene restoration do not have that floaters. And our interactive simulation is also great. For the object scene interactive simulation, as shown here, since we have filled out the holes, so the box can bounce out of the scene. For the multiple objects, we can also restore well. So our work can be used from one scene to another scene to support more variety of data sets. We also do some quantitative evaluations. That is the subjective metric user study. Also, we conduct some objective evaluation. We compose the complete real scenes and real objects, and that is our results. As shown, we show some ablations. Okay, what can concluded is that our task try to restore the object and context scene to simulate, and we don't rely on 2D impacting models to repair the broken geometry. We can to scan our project website by the QR code to see more details. Thank you.